right. Is that dim?
It looks great
Does that
from
look
my
dim?
point of view.
Okay.
No,
I don't know
looks
what's
good.
happened, but anyway. So I'm a Masters of Science candidate at the University of Melbourne. Studying applied crypto. It's a Master of Computer Science. It's all a little bit fuzzy, but I'm having a good time, and that's the main thing. If you want to contact me, this is my little CV site. You can also reach me on Twitter here. So us cryptographers tend to be a little bit of a theatrical bunch. So I've decided that my talk will be separated into 3 acts. And the first one is a tale of 2 families. 2 households, both alike in dignity, in fair Canberra, where we lay our scene. We have Alice and we have Bob. They want to talk to each other, but their families hate each other, so it needs to be a secret. And we're going to look at how you can keep a secret in the digital age. So they want to say hello to each other, but it needs to be a secret. So we're going to hide their message, make it look like this. Hopefully no one else can read that. So we're going to get started. What is a crypto system? Well, first you have to generate some keys. You may have an asymmetric crypto system where one key encrypts and the other decrypts. We'll return to that idea later. Or you may just have one secret key for a symmetric system. Now, you also need to be able to encrypt a message with the relevant key, and we call an encrypted message a ciphertext. Finally, you need to be able to decrypt that message, otherwise it's not a very useful crypto system. So you can recover the ciphertext, you can recover the message from the ciphertext, but only if you have the secret key, well, hopefully. So we would like it if a crypto system can't be broken. And we say that a crypto system is information-theoretic secure if no adversary can recover the message unless they have the secret key. So this is what we would like. And let's take a look at one way you can do this. An example, if you have the secret key, don't choose this as your password, but just for sake of example, if you have the secret key, ABCDE, you can use bitwise XOR. You XOR these 2 strings together, and you get an apparently random, this is in hexadecimal, you get an apparently random sequence of bytes as output. And it's information-theoretic secure. This scheme satisfies that really strong notion of security that we'd like. And that's because if you don't know the secret key, you have no idea what message it is. If I thought the secret key was this string instead of ABCDE, I would get out the message frogs, but it was not frogs, it was hello. So it's information-theoretic secure because you have no way to know which actual message was used. You can only do it if you've got the secret key. So that seems pretty nice. Why don't we all use information-theoretic schemes? Unfortunately, first of all, no asymmetric crypto system can be information-theoretic secure. Now, this is a theorem of cryptography. I'm not going to go through it. It's quite a long and involved discussion about that. But if you want to have a public key that you don't already agree, so if you want to have a public key that everyone knows, you don't have to already agree on a secret key. You don't have to meet up somewhere and say, hey, this is my secret key, don't tell anyone. So that's not ideal. We like asymmetric cryptography, and again, we'll come back to that later. But it gets worse. If you want your crypto system to be information-theoretic secure, the secret key has to be at least as long as the longest message. So you can't hope to have information-theoretic security unless your secret key is really, really long. And I'm sure you can imagine why that's problematic. If you want to share, say, a 2 gigabyte file that maybe some authorities would not like you to share, you need a 2 gigabyte secret key, it gets unwieldy and it's not an ideal outcome. So unfortunately, information-theoretic security is not really the go most of the time. You can see these sad faces. They are not pleased about this. This moves us to Act 2. And in Act 2, we ask, are you feeling lucky? So what we're going to settle for, we can't have perfect security. We can never have this situation where no one can recover the message without the secret key. So we settle for something just a little bit weaker. We call this computational security. And a system is computationally secure if no efficient adversary, one that runs in a decent amount of time. Obviously, if your adversary is given 1 billion years, then we don't really care if they can break the system because the sun's going to die before then. So we say it's computationally secure if you can't do it efficiently, unless you're really lucky. And this is the get out of jail free that's going to stop us from running into that problem with information-theoretic security. Unless you're really, really lucky, there's no way you can recover the secret key. And you may be wondering, okay, well, what does extremely lucky mean? Luckily, we've thought of that. And this is some mathsy stuff. If you're not from a maths background, don't worry about it. The idea is we want the probability to be negligible. And that means smaller than the reciprocal of any polynomial. In other words, it goes to 0 really, really quickly, faster than any polynomial, x squared, x cubed, whatever you like. So we're going to say, if you're really lucky, sure, I guess you can get the message, but you have to be extremely, extraordinarily lucky, and we'll say that's good enough. So the next thing that we think about, well, okay, we have this notion of security. We've agreed, okay, we can't have no adversary recover the message. We're going to settle for it being really unlikely that they can grab the message back out. How do we prove that a system has this property? And, we can make lots of strong arguments. We can say, well, look, it has this thing, and we know that this is a hard problem to do, so they should be able to break it, right? Now, a cryptographer like myself, or a cryptographer in training, thinks to themselves, that's not good enough. We need a rock solid proof. We need a strong, convincing argument that our system really does have this property. Otherwise, you could think of all sorts of schemes that maybe have the property, but it's not good enough. It's not good enough to protect valuable secrets like your bank account or, those really embarrassing drunk party photos that you posted as a teenager. We need something better than that. So we start to think about games. The idea is the challenger and the adversary are playing a game against each other. And the adversary wins this game if they can break the system. So we're going to play a game. Hopefully the adversary can't win. We'll see how we go. Now, one basic such notion, if Alice is sending a message that's either 0 or 1, so 1 bit to Bob, someone watching them shouldn't be able to work out which one Alice sent. So Alice has sent one of the two. You shouldn't be able to work out which one she sent. That seems like a useful property to have. Let's look at how we can make that formal. We call this the indistinguishability game, or indistinguishability under multiple encryptions is an extension. The idea is two ciphertexts, remember an encrypted message, two ciphertexts should be really hard to tell apart, or it should be hard to tell what corresponds to what. So here's how we're going to do this. First of all, our challenger C is going to run the generation algorithm. They're going to generate a secret key. And the adversary is going to think of two messages. They're going to say to the challenger, you're going to encrypt one of these two. I don't know which, but you're going to encrypt one of them. And the challenger says, yep, all right, I'm going to flip a coin. If it comes up heads, I'm going to send the first one encrypted. If it comes up tails, I'll send the second one encrypted. And now the adversary has to guess which one the challenger sent. So clearly, if they can win this game reliably, they have broken this indistinguishability property. They can tell whether the challenger encrypted 0 or 1. They can tell whether Alice sent 0 or 1 to Bob. So the way we're going to think about this, it's all well and good to think about, okay, we want this game to be hard to win. But again, we like to make it formal. We like to make it rigorous, present a convincing argument. So what we're going to say, if any polynomial time adversary, and remember, if it's not polynomial time, it takes forever, so it doesn't matter. If any polynomial time adversary has a probability of less than a half plus a negligible amount. Now, you might be thinking, didn't we want it to be negligible? Well, I mean, think about it, right? The adversary could just toss a coin, and half the time they're going to happen to toss the same result as the challenger. So we say instead, all right, they've always got at least a 50-50 chance of guessing. So we're going to say it's barely better than 50-50. And if any adversary, no matter what, has only a tiny bit better than a 50-50 shot at winning, we say it's indistinguishable secure. And this is a pretty desirable property to have. It's not the be-all end-all, and we'll see an extension of it later, but it's a good starting point. And you can already see how cryptographers think about security, right? It's all about these games, these chances, these probabilities. We model an interaction and we think about how likely is it that we can break it. So let's do an example. We're going to pick a simple crypto system. This may be one that some of the audience may be familiar with. We're going to pick a number between 0 and 25, and that's going to be our secret key. To encrypt a message, we'll rotate the letters rightwards by that much. And if we go off the end, we'll just go back around. So if our secret key is 2, Y ends up at A, Z ends up at B, and so on. Otherwise, here's an example. We take hello, we encrypt it, and we get this little random looking string. You may already be thinking, well, it's not really random looking, right? If this double L got mapped to this double N here. We'll come back to that. But for the time being, let's think of an even simpler reason that this crypto system is broken. What's the probability that you can decrypt the message? What's the probability you can get the message without knowing the secret key? Well, ideally, you have to guess randomly between 0 and 25. But the problem with that is a 1 in 25 shot is not that small. So this system is already broken, but we'll use it to illustrate how to reason about such systems. So if we play the game, our challenger is generating a secret key, in this case 2. The adversary is going to send 2 messages to the challenger. In this case, the adversary chooses AB and AC. Now the challenger is going to toss a coin. They got heads. So C, the challenger, is going to send the encryption of AB, which in this case is CD, to A. All right, we've got an encrypted message, AB, which looks like CD. Now A goes, CD, the letters are 1 apart. If they had encrypted AC, the letters would be 2 apart. So A, the adversary knows the challenger must have chosen the first message. So the adversary can just say, all right, first message, and they always win. So this system, which we call the Caesar cipher, because it was at least apocryphally, I'm sure some ancient Roman historian is out there cursing my name. We call it the Caesar cipher because Julius Caesar used it in ancient Rome. And it's not indistinguishable secure. It fails this desirable property. And it's useful to think about why. And the reason we broke this is the relationship between the messages AB and AC, the distance between the 2 letters. That relationship was not broken, okay? It was preserved when we encrypted it. The relationship stuck around, and the adversary could use that to break the system. Now, we call this oh, there's a typo here. That's embarrassing. We call this a chosen plain text attack, hence the header, right? And the idea is the adversary chose what plain text to use, and because they knew it, they could break the system. Now, a real-world system like AES, for example, in the Galois counter mode, or like RSA, when it's used in practice, the important part is when it's used in practice. Real-world systems are not vulnerable to chosen plain text attacks. And it's not too hard to see why. If you're looking at a HTTPS connection, a secure connection encrypted with a nice symmetric key, the first message, a lot of the time, it's going to start something like get/http/1.1. So you already know a little bit of the message that's being sent. If your system is vulnerable to a chosen plain text attack, that's not a very practically useful algorithm, because a lot of the time, either you know the whole plain text or you know at least a little bit of it. So we ask a little bit more about systems. Yeah, if you use them properly. Okay, so unfortunately, as I'm sure if you've ever experimented in the space, you might know, it's very easy to mess up some of the assumptions made. So for example, AES asks you in the CBC mode, AES asks you, give me a random set of values to initialize with. If you forget to give it a random set of values, it will be hopelessly broken. So they're not vulnerable to these attacks, but you need to make sure that you follow the assumptions made by the systems. All right, we'll come back to that at the end of the talk. So Act 3, as promised, we're returning to public keys. So if you're not familiar with the idea of a public key, the first widespread use of it was in the 70s when Rivest Shamir and Adelman, I always mess their names up, invented the RSA algorithm. And this is the classic algorithm used for public key cryptography. It's still used a lot of the time today. There are differing opinions on whether that's a good thing, but it is a vitally important historical algorithm. Now, the idea is Alice and Bob can talk to each other without having agreed on a secret key. And that works. They have public keys. So Alice has a key A, and she tells everyone the key. Everyone knows this public key A. And similarly, Bob has this public key B, which everyone knows. But only Alice knows the corresponding secret key or private key that can decrypt those messages. So anyone can send a message to Alice, anyone can send a message to Bob, but only Alice can decrypt her messages, and only Bob can decrypt his messages. So for example, Alice may send the message, "How are you?" encrypted with Bob's key. Bob can decrypt that, read it, and send the response, "Good, thanks, you," encrypted with Alice's key. Now, this is a different cryptographic model. It has its advantages and disadvantages over symmetric cryptography, notably that this is usually a lot more computationally intensive, but they both have their uses. Now, I'm going to focus on public key cryptography because I think it's more interesting. I'm biased here. I think it's more interesting. Symmetric encryption is super interesting too, but there's a lot less theoretical depth behind it. So here's a better game. Remember last time that the adversary won because it knew something about the plain texts. And I'm going to argue this is a better game because we're going to encode that into the system. We're going to make the assumption the adversary can always encrypt a message. They are always able to take whatever message they want and discover what its encryption is. And if our system is secure with this stronger assumption, well, it's a stronger system. So it's exactly the same, you might notice, as the Indistinguishability game, with one little addition. The challenger runs the generation algorithm. They get a public key and its secret key. The challenger gives the adversary the public key, and also it gives it access to the encryption algorithm. So we're not even assuming how it works as a secret. We're telling the adversary, hey, here's the algorithm. If you want to encrypt a message, knock yourself out. Now, the adversary with this information is going to send two messages, whatever it likes, to the challenger. The challenger is going to encrypt one of them according to a coin flip, and the adversary is going to try to guess which one got encrypted. And again, we say exactly the same thing. If they have only a tiny bit better than a 50-50 shot at winning, it's CPA, indistinguishable chosen plain text attack. Secure, all right? So it's a stronger guarantee if we can prove our system is secure by these terms, then we've got a stronger system. And this is something I want you to think about if you're not a cryptographer. We have different guarantees, different types of security. Some of them are stronger than others. So, there is no one definition of security. It depends a lot on your model, just like anything else in cybersecurity. All right, so we're going to end by seeing how to prove a system satisfies this chosen plain text attack security. But first, we're going to have a little bit of maths. If maths isn't your forte, I apologize. You don't need it to follow the essence, but if you're curious, read on. So modular arithmetic, it works like a clock. You've got a clock, it points at 5 o'clock. You add 8 hours, you end up at 1 o'clock. And the way that works is we do our addition and then take the remainder modulo 12, all right? So this mod thingy here, if you're used to programming, a lot of programming languages use a percent here. The modulo operation says divide by 12 and take the remainder. So divide 13 by 12, you get 0 with 1 remainder. That remainder is 1, so our result is 1 o'clock. We call this addition modulo 12. It's just fancy name. And it turns out that raising things to powers is one way if you do it right. So if you make the right choices, raising powers is one way. You know G, you know Q, and you know that y is equal to g to the power of x. Oh, that should be p. Y is equal to g to the power of x mod p. Then it should be hard to guess x. So you know all of the ingredients. You know you know this base number g, you know the final result y, you know what we're taking the modulo of, but you don't know x, it's hard to guess x. So we call this the discrete log problem, and it's the basis of a lot of modern systems. It's not too hard to grasp, so it's a nice one that I thought I would choose. So with the right numbers, there's a little explanation of what I mean by that down here. There is a lot of complicated reasons why that is the case. So hard to guess. Again, that's a pretty loose term, and we want to define what that means formally. We want to have a convincing argument for what that's supposed to mean. So we call this the decisional Diffie-Hellman game. And the reason for that is because there's a system, Diffie-Hellman or DH, which is used to agree on keys, and it relies on this assumption. So we call it the decisional Diffie-Hellman problem. And the idea is the challenger chooses 3 powers, A, B, and C, tells the adversary g to the power of A and g to the power of B, and then either g to the power of AB or g to the power of C is sent to A, the adversary, and then the adversary has to guess which one was sent. So the idea is if you could guess x, if you could undo this exponentiation, then it's easy, right? Just undo the exponent. If it's AB, sweet. If it's not, then, well, you know which is which. So given that exponentiation is hard, it should be hard to do this. So if it's hard to do this, we say, all right, this is a strong basis for our security. And some of you might be thinking, well, why do we have to assume that this is hard? How do we prove that? The answer is, I don't know, and neither does anyone else. It's quite difficult to figure out whether problems are hard in computer science, quite a fundamental problem that we keep running into. So a lot of the time we just assume something like this is hard, and if someone manages to break it, well, you know, there's quite a big incentive to break it. So if someone manages to break it, then we'll move on to something else. But for now, this seems pretty sacrosanct. If you make the right number choices, it is very hard to undo exponentiation. Now, we can turn this into a crypto system. We've got a one-way function, something that's hard to undo if you don't know the secret. So we're going to pick a random number x, that's going to be our secret key. Another random number, well, take g to the power of x, and we end up with y, which is the public key. And remember, it's really hard to undo this, right? If you don't know x, it's really hard to guess what it might be. So we can tell everyone what y is, and it'll just look like a random number to them. If we're going to encrypt a message, some details, pick a random number, output this thingy, which is a pair of numbers. If we're going to decrypt it, well, because we know x, we can take the first thing, raise it to the power of x, and then we can just divide through and we end up with a message. So crucially, we had to know x. If we didn't know x, we couldn't raise this to the right power to make it cancel out the y, all right? So this is the Gamal crypto system. It's one that I'm quite familiar with and quite fond of. I'm using it a lot in my research. So here's the grand finale. We're going to show if you break Gamal's security, then you can break decisional Diffie-Hellman. And that might sound a little bit strange. Isn't decisional Diffie-Hellman meant to be hard? Exactly. The point is, if you could break Gamal, then you could break decisional Diffie-Hellman. But you can't break decisional Diffie-Hellman, so you can't break Gamal. It's a proof by contrapositive in the mathematical jargon. So we're going to try to break decisional Diffie-Hellman, knowing that we can already magically break Gamal. We have been given g to the power of a, g to the power of b, and we're given one of these two things, either g to the ab or g to the c, but we don't know which one. Our job is to work out which one was sent to us. So we're gonna grab Alice. Hello, you're part of this now. We're gonna play the indistinguishable CPA game with Alice. But instead of letting her encrypt things, we're secretly gonna give her this fiddled function, right? I should have put m times y to the power of b here, right? Should have given her that. But I'm gonna give her x, which is either g to the power of ab or g to the c. And she's gonna be none the wiser. And notice that in this case, if our secret key was A, then, well, g to the power of AB is the same thing as public key to the power of B, which is what it should be. So if we really were given g to the power of AB, this really is encryption. But if we're given g to the power of C, that's some random number So this isn't encryption. Alice doesn't know, but it's just complete garbage. So if Alice wins the game, if Alice can decrypt this message, decrypt this ciphertext, recover the message, we're going to guess that we got g to the power of c. I got that backwards. We're going to guess that we got g to the power of ab. Otherwise, guess g to the power of c. So remember, we're giving Alice this fake encryption function, and she's going to try to break it. If x equals g to the power of c, Alice doesn't see a real encryption, so she has no hope of winning. The best she can do is guess randomly, so we're also just going to guess randomly. But if x is g to the power of ab, Alice sees a real encryption of her message. That means she wins more often than not, right? A little bit more than a half. And we said that Alice could break Gamal. We assumed that we could break Gamal. But decisional Diffie-Hellman is hard, so there's no way that Alice can win more than a tiny percentage of the time above a half, right? The fundamental idea is, if Alice could break the system, then we could break decisional Diffie-Hellman, but we can't, so she can't. And that means that the Gamal system is ind-CPA secure if we assume this Diffie-Hellman assumption, which is, it has quite a lot of empirical data to back it up by this point. So the conclusions that I want you to take away, especially if you're not a cryptographer, if you're not a mathsy type, cryptography in most of the time in practice is probabilistic. So we're not saying you can't break it, but we're saying you can't break it in any reasonable amount of time unless you're really, really lucky. Now, another thing is we're really sensitive to the assumptions that we make. I already said that AES in CBC mode, you have to give it a random bunch of data to start with. If it's not random, then you're busted. Similarly, if you can solve DDH, if you choose the numbers wrong, such that you can guess the difference between the two things, Gamal is completely broken, right? We only proved it was secure if you assume this property. And also, you need to read the specification carefully. It's going to tell you exactly what is and isn't allowed. You're going to be told, okay, well, you have to pick a particular prime number with this certain property and make sure that for your G, you don't pick a dumb number, and so on and so forth, right? So make sure you read the spec really carefully and don't try to implement it yourself. This is why we say there are so many not hidden, but there are so many difficult assumptions and fiddly details. Don't try to do it yourself if you can avoid it. And perhaps the most important thing, crypto is really interesting. The details of how all these things work and how we convince ourselves that they actually work is super fascinating. And it's worth a read, even if this isn't your main area, because we rely on it so much. TLS, HTTPS, DNS security, so many things rely on cryptography. And if you're interested, here are some cool references that I can highly recommend. And that is all. I hope you learned something. I'm going to turn off the slides in a sec.
Well, thank you very much, Eleanor, for that talk. We'll just wait for Kylie to come back on. We do have a couple of questions. We have one from the Slack. And just a reminder for everyone, we do have a Slack channel, hashtag #CSides on the BSides Canvas. Slack. Go to the webpage for CSides, bsidescanvas.com.au, and you'll be able to get the details to log into that Slack. But the question on the Slack was, what are your thoughts on post-quantum cryptography, and what are your thoughts and experiences? Is it going to change the world? Are we safe? Are we safe from these quantum computers?
Yeah, woohoo! So that's obviously a really hot topic at the moment, both inside crypto and outside crypto. Everyone's interested. A quantum computer is going to steal my credit card. The answer is maybe, but probably not yet. So the reason, if you're not familiar, quantum computers use a different approach to computing, or we think it's different at least. No one knows for sure yet. They use a different approach, and that means that there is actually an efficient algorithm that can break RSA, and there is an efficient algorithm, a variant of it, can also break Gamal, for example. So the question is asking, you know, can we use this to, are all our secrets doomed? And the answer is, well, not yet. And the reason is you need a really big, really stable quantum computer to effectively run these algorithms. Last I read, they were able to factor, I think 8 to 10-bit keys was the best anyone's done. And modern RSA uses 2048-bit keys. They've got a while to go yet, and classical computers are actually much better at breaking RSA than quantum computers at the moment. But if we have a sudden breakthrough and large-scale quantum computers become a reality, then we need to shift our thinking, come up with other ideas. And the good news is a lot of really clever people much smarter than myself, Ron Steinfeld at Monash is one of them. They've done a lot of work on systems that are safe, even with a quantum computer. If you're interested, the keyword is lattice cryptography, lattice, Lattice.
I suppose like a follow-on to that question, just sort of this is like, I mean, it's quite a broad question, I suppose. I mean, do you see cryptographic research now as sort of, you know, at a sort of a, not much research is happening, or is it like a period of lots of research happening? I mean, you talked about asymmetric crypto in the 70s being introduced. As you know, we've got, you know, block ciphers, we've got stream ciphers, we've got asymmetric crypto. Is it all over, or we've got a new world of crypto that's waiting to be invented and defeated as well?
Yeah. Vitally important question. So the way I see it is symmetric crypto is mostly a solved problem from my perspective. Symmetric AES works fine. No one's found a really good attack against it. Not very interesting. Similarly, Diffie-Hellman works really well unless you have a quantum computer. RSA works fine. We have better algorithms using elliptic curves nowadays, but you know, all of that stuff, the fundamentals, fine, solved problem. Where it gets really interesting is applying these ideas. So in the last decade or so, there's been a huge amount of research on what are called zero knowledge proofs. And the idea is, I know some secret value. I'm going to prove to you that I know the secret. I'm going to prove that I know the secret key, but I'm not going to tell you anything about the secret key. So that's one really active field of research at the moment. How do I prove more and more complex things? It's relevant to, I fear to say the word, but it's relevant to blockchain research as well. Because, well, how do you verify a Bitcoin blockchain? You start from the beginning, check the first hash, check the second hash, check the third hash. It takes forever, and the blockchain is huge. I think it was like multiple terabytes when I last heard. So a lot of research is focusing, how can we prove facts? How can we prove things are legitimate in more efficient and more flexible ways? So that's one thing. The other thing, post-quantum crypto, there's a huge flurry of people working on what are some future-proof quantum mechanisms, future-proof crypto mechanisms that might replace the ones we've got. So I'd say it's a very active field, but we've moved away from a lot of the more foundational stuff.
There was an extra question on the Slack from Maybe here asking if Eleanor has any favorite PQ systems that are cool and or should win. Yeah.
So I am woefully underread in the area, but lattice systems are really exciting. The idea behind it is you have a linear algebra problem. So you've got a matrix and you've got a matrix equation. And the idea is you've got to find a solution to the matrix equation, but not just any solution. It has to be a solution. And remember, we're solving for a vector, so a list of numbers. It has to be a solution with a really small magnitude. So if you add all the numbers up, it has to stay quite small. And that's interesting to me because with Gamal, it's like, well, if you guess the secret key, the game's up. With a lattice system, it's not, you can't just guess one possible answer. You have to guess an efficient answer. And I think that's really exciting that there are lots of possible secret keys from one perspective. I think that's really interesting and shows a lot of promise, but post-quantum is super not my area, so don't quote me.
Awesome. That was great. That was great. I don't think there are any more questions on the slide. No more
feel
questions
free
on the
to-
Slack, but I
Yeah.
think a lot of people are clapping and cheering and talking about your talk. So probably head there if you can, and
Will
good
do.
clapping, Sylvia.
Thanks, crew.
Yeah, awesome.
Check
Thanks
it out.
again
So
for
already
speaking.